Hey, it's Mr. Staltano. This video is going to explain double replacement reactions. So, in a double replacement reaction, the generic equation is AB plus CD reacts to form AD plus CB. So in other words, one of the giveaways is that you have to have two compounds for this to happen, two chemicals that have at least two capital letters each, to form another two chemicals that have at least two capital letters each, essentially. And all that's happening is there's a simple swapping happening. So in our example here, we have a couple dancing and another couple dancing. And then after the reaction, they switch dance partners so that each person is now dancing with somebody else. In our chemical example up here, we've got sodium with chlorine, so Na with Cl, Ag with F. And then after the reaction, now Na is with F and Ag is with Cl. So we just have a swap that's happening there. That's all that's happening. Another important thing to note is that the metals always remain at the beginning. So notice how in our generic it was AB plus CD goes to AD plus CB. The A's had to stay to the left. A and C both had to stay to the left because they're the metals. Same thing up here. Sodium remained to the left of the formula. Silver remained to the left of the formula even though they changed into new compounds. But it's a simple switch to make two new compounds essentially in a double replacement reaction. Here's another example where you have the penguin with the hat, the pig with the glasses. After the reaction, now the penguin has the glasses and the pig has the hat. So just a swap over the course of the reaction. So here's another example. Here's a real-life chemistry example of a double replacement reaction. And what you're essentially having is we have a colorless solution of lead-2 nitrate. So it's a solution. It's an aqueous solution. So in other words, we have lead nitrate dissolved in water, and it's reacting with potassium iodide also dissolved in water. That's another hallmark of this type of reaction, is you have to have two aqueous things, two aqueous ionic compounds that are, so in other words, they're both dissolved in water in order for this to work. And then as a result, what's happening in this reaction is you get aqueous potassium nitrate. So notice how the K has switched with the lead, the Pb. And this new substance is still dissolved in water. And something else we formed is not dissolved in water called lead-2 iodide. So now the Pb is with the I, and that new compound that formed does not dissolve in water. So that's a solid that formed. So let's take a look at what that actually looks like. Here we have two clear solutions, both relatively clear. And then when you put them together, you see that yellow kind of cloudiness that's forming. That yellowness that wasn't there before is the solid that's forming. You can also see it in the picture up here. So in the picture up here, there was clear liquid in the graduated cylinder, clear liquid in the beaker, and when they come together is when they form that new lead-2 iodide, which is a solid. So that cloudiness is formed because a solid is there. That's an indicator that a reaction has occurred. And the term for that is called a precipitate that formed. That's what that solid is called. So in this case, the precipitate that formed was lead-2 iodide. So let's take a look at what's happening sort of at the chemical level to make this occur. So before we start our reaction, take note that we have lead-2 nitrate, right over here, PbNO3. That's aqueous, right? So it's dissolved in water. That's one of our requirements for this kind of reaction. And anything that's dissolved in water is going to be ionized. So notice how it's broken apart into Pb and a couple of NO3s, right? That's what this 2 means, that there's a couple of NO3s. And they're floating around as charged particles. They're no longer together as a result of being dissolved in water. That's important. Same thing with potassium iodide. Instead of being together as Ki, it's split apart and ionized as it dissolved in water into K plus and I minus. So that's why this is aqueous. So that's why both of these need to be aqueous, because they need to be split apart sort of in order for this dance to work, right? In order for these partners to switch partners, they have to be broken apart, and water helps that happen. If these two weren't in water, they wouldn't be floating around separated like this. They would be solids and still bound together. So let's watch what happens. So we pour our two clear liquids together because they're both aqueous. And we're going to zoom in to see what's happening at the chemical level. And now we're seeing that the opposites are attracting. So the Pb2 plus that was with the NO3 before is starting to get attracted to the I's. And they're actually joining together to form a yellow solid. So when Pb finds I, that no longer dissolves in water, that new compound. But if K and NO3 find each other, they don't really stick together, and that doesn't. They still dissolve in water essentially. They're still aqueous at that point. And so here's our overall equation where we have aqueous lead 2 nitrate, aqueous potassium iodide, right? Both dissolved in water, like we said. Our yellow precipitate at the bottom, our solid, is the lead 2 iodide that formed, and the potassium nitrate, the KNO3, is still aqueous. So in other words, this clear liquid up here, there's KNO3 dissolved in there. That's what's happening there. Because KNO3 is still what we call soluble. It still dissolves in water. Whereas lead 2 iodide is not soluble. It does not stay dissolved in water, and that's why it appears as a solid. Because we made a new substance that in itself no longer dissolves in water, it appears. It just comes. It crashes out of the solution as a solid essentially. So there's a way for us to be able to predict whether a reaction will happen in a double replacement reaction without actually going all the way through it. So let's look at our example we just did. This is a solubility chart, by the way, so this will tell you whether something will dissolve. So in other words, if the combination of the two things will be aqueous when we look at where they meet on the table, or if the new substance won't dissolve anymore, if it'll form that solid precipitate. So let's look at Pb and NO3. So Pb is right here, and with NO3, that is aqueous, which makes sense, right? That dissolves in water essentially. And let's look at K and I. So here's K plus and I minus, and that also dissolves in water. So that's aqueous, so that makes sense because they were both aqueous when we started. Now we look at K and O3, K, and then compare it with NO3. So NO3 is over here. So when we look at where they meet, it's right here. That's still aqueous, so that still dissolves in water. And then we have Pb with I. So that forms a solid. That's a precipitate. So this is one of the biggest things. If you form a solid, that means this double replacement reaction did happen because we formed a new substance. That solid didn't exist before, right? We suddenly had this yellow substance we never had before. If you form a solid precipitate, that means this double replacement reaction did in fact occur. But just like with other reactions, just because you throw two things together doesn't mean a reaction will always occur. So let's look at a counterexample. Here we're reacting NaOH, so let's verify that Na, and you don't have to do this for the reactants every time, but we're just showing how the table works. Really, you're always just looking at the products. But we'll verify, so Na, and then here, if we see it with OH, that is aqueous, so that will dissolve in water. Okay. K and Cl, also aqueous, so that will dissolve in water. Check, check. Let's see how KOH is. K with OH, that also dissolves in water, so I'm going to put an aqueous there. And the other product that would potentially form is Na and Cl. So that also is aqueous. So this is actually no reaction. If everything is aqueous, that means you didn't form anything new. Remember before we formed a new solid? That's not what happened here. Remember when we looked at that zoomed in portion and the part that was aqueous was still ions, charged particles that were floating around? That's what's happening here on this side. So imagine like on the left side, we have Na plus, OH minus floating around, K plus, Cl minus floating around. Because nothing came together, you still have those same pieces just hanging out, floating around. Nobody bonded with anybody else, and so you didn't form a new substance that way, essentially. So these products that we have listed here actually never really form. They never really end up sticking together. But the biggest thing is if you see all aqueous, no reaction. That's our indicators. And this is only used for double replacement reactions. That's the only time you use this solubility table. So if we just wrap up here, here's a couple of examples. So here's our double replacement reaction formal definition. Reactions involve an exchange of positive ions between two reacting compounds. In other words, they're positive guys swap dance partners. Here's an example. We see aqueous, aqueous, solid, aqueous. This guy is our precipitate, our solid that formed, so yes, reaction happened. Aqueous, aqueous, gas, and aqueous. Yeah, that formed a new substance. We formed a new gas, so check, reaction happened. Aqueous, aqueous, and aqueous, but a liquid is formed, check, that reaction happened. So as long as you didn't form aqueous and aqueous, you did form something new, and a double replacement reaction did in fact occur. So the definition, general reaction between two ionic compounds with one product precipitating from the solution, so in other words a solid being formed, or escaping as a gas, or water being formed as one product. So that's what we're looking at. So that's it for double replacement reactions. Thanks for watching. Remember, chemistry is everywhere.